Namaste, welcome back to Sthita Pragna channel. You are watching episode 4 of chapter 1 Data Engineering. Welcome back. When you think about scale on internet, what comes to your mind? Seriously. I mean, at least back then, Google. Right now, we never know if it is Facebook or some other thing, but Google instantly comes to mind, isn't it? Even today. Their mission to index and search the world's information created a unique set of technical challenges far beyond what traditional databases or imperative programming could handle. So, Google engineers came up with new tools, and when they came with those new tools, and they called one of them GFS. What is that? Google File System. What is this? This is for fault tolerant storage. And then they came up with another one, which is Big Table for structured storage. And the famous MapReduce for parallel distributed computing. This blueprint inspired the open source community, especially at Yahoo, and led to the birth of Hadoop. Actually, there was a very big story. As I said, Doug Cutting, and there was another one of his partner. They were working on a search engine as well, just like Google, but they immediately faced a problem which is about the scaling. They couldn't index all the websites that's available on the internet, so they were just trying to see if there are any other ways. And guess what? Google released these papers for the storage, Google file system, big tables, and MapReduce. And by the way, by that time, Google already had this technology for 10 years. So only after 10 years, they released the papers, only papers, how it works, not the technical code and whatnot. Then duck cutting and etc. They used those papers and created what we are using, which is MapReduce and Hadoop. It was not named Hadoop. The name Hadoop came when duck cutting's son was playing with a elephant, toy elephant, and the kid was saying Hadoop, 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 and then he heard it, and then he decided, let's name this Hadoop. So yeah, the Google file system became Hadoop distributed file system. MapReduce became MapReduce, and Bigtable, I think this became HBase. If I'm not wrong, correct me in the comments if I'm wrong. So that's where it went. And MapReduce, and later with Map, I think the Hadoop 2.0 came on. We'll talk about that in a minute. Now let's look at how a typical data processing workflow runs on Hadoop or MapReduce. We have already seen this, but let's assume that we have our data source sitting here. Uh, let's call it like database or something like that, a container. And HDFS reads. Okay. Then you have your MapReduce. HDFS writes. Right? This is your HDFS MapReduce is reading from it, then writing to HDFS again. And then you have that's your HDFS, let's assume. Then you will have again MapReduce, reads another MapReduce writes to another location. So typically this is how it looks like. Right? Data is loaded from HDFS. MapReduce processes the data, writes back to HDFS, then next MapReduce reads from HDFS, process and writes back out. This process repeats for every stage in your pipeline. Okay, notice the alternating pattern. Read from disk, process, write to disk, over and over and over again. While this approach made fault tolerance easy, why? Because intermediate results are always on disk. But it introduced a big problem. What is that? Disk I/O, input output, that became the bottleneck. Every read and write to disk slowed down your processing pipeline, especially for iterative algorithms or multi-stage workflows. This meant some jobs could take hours or even days to finish. But you think that's the only headache? Nope, there were others. MapReduce jobs required lots of boilerplate code and setup. As I mentioned, the word count example we have seen, it would take at least 100 lines of code because of some boilerplate code you have to write for all the MapReduce jobs. And the next one was managing and administering Hadoop clusters was complex, and batch processing was the only game in town. Machine learning, streaming, SQLite queries needed entirely different tools, each with their own APIs and configs. Like Facebook created Hive, somebody else created Storm, and I think Cloudera created Impala, etc. All this made big data projects hard to develop, maintain, and scale efficiently. Now, of course, our hero enters into the picture, the Spark, which was born at UC Berkeley, the college, Berkeley College, you might have heard about. They had a lab called AMP Lab. So in 2009, here the Sparks creators, they set out to fix the bottlenecks that MapReduce had and also the complexity of MapReduce while keeping all the good stuff MapReduce had, like distributed fault tolerance and data locality. But how did they do it? How did they manage to do it? Well, first of all, instead of writing to disk, they came up with in memory. Why is that happening? Processing, right? Spark keeps data in memory between operations whenever possible, cutting out the slow disk I/O that plagued MapReduce. Then, instead of using multiple tools created by a bunch of companies, you will have a unified engine, right? One tool for batch, streaming, SQL, machine learning, and graph analytics, all with simple composable APIs in your favorite languages like Python, Scala, Java, and R. And this was simpler as well as faster. How? Because Spark jobs are much faster than Hadoop MapReduce, sometimes 10 times, sometimes 20 times, and sometimes they claimed it 100 times for many workloads, and sometimes even more. And it was scalable and fault tolerant. Maybe this is similar to MapReduce. Spark distributes your workload across thousands of commodity servers and can recover automatically from failures using its core abstraction, which is called RDD, Resilient Distributed Data Sets. Don't worry if it sounds scary. We are going to talk briefly in our beginner uh, playlist and in depth in our intermediate playlist. And finally, ease of use. With high level APIs and powerful modules, Spark makes big data accessible to engineers and data scientists alike. Right? You might be thinking, how? Give me examples. We only understand with examples. Sure, why not? For example, in the Daytona Gray Sort competition, Spark sorted 100 TB. You know TB? We have MBs, we have GBs, then we have TBs. So it sorted 100 TB of data 3 times faster than Hadoop MapReduce. And guess what? Using only a tenth of the servers. If MapReduce used 100 servers to sort this in 3 hours, we only used 10 servers and we sorted it in 1 hour. See, that's our superhero. And that was using just disk based operations. So, see, blow after blow, man. We are not even using in memory, we are using disk. If we leverage in memory power, imagine how fast we would have done. So, Spark wasn't just an incremental improvement, it was a leap forward, making big data faster, easier, and much more flexible. What does all this mean? Well, Spark lets you process massive data sets quickly and efficiently, whether you are running on a single machine, a cloud cluster, or an enterprise data center. It handles failures gracefully with built-in fault tolerance and automatic recovery, and it simplifies your data pipeline, letting you use one engine for almost everything. No more endless disk reads and writes after every step. No more stitching together a dozen tools. Just fast, unified, scalable analytics on any data at any scale. Right? So let's start some other topic. Not some other topic, a continuation of this. We are going to dive right now into the core of what makes Spark so powerful and popular for big data processing. We have just covered it, but we are going to cover more items. If you ever wondered how Spark crunches massive data sets so quickly, or why our big brother RDD, yes, RDD is like a big brother, you will know why, are at the heart of it all, just stick around. You are about to find out. Now, let's start with what makes Spark lightning fast. We have learned here, we have seen an example like, oh, it is 10 times, 20, 100 times. We said simpler, faster, but why faster? Did you think, oh, this guy is saying faster, but he's not explaining why? Well, now let's talk about how or what makes Spark lightning fast compared to traditional systems. One reason you already might have thought about it, because it processes all its data in memory, meaning it doesn't write data to disk between every step, which is a huge time saver. But that's not all. Spark also uses several optimization techniques. What are those? Lazy evaluation. And you might be thinking, you said several optimization techniques and you're talking about being lazy. If Spark is lazy, why is it optimization? Don't worry, we'll talk about that. And then we have something called predicate pushdown. And note these down. They are important in interviews. If you use these words, they will be pleased. And then finally, partition pruning. Okay? These three optimization techniques. We will unpack these techniques in detail in upcoming videos. Don't worry about it. But the big idea is that Spark does as little work as possible to give you the results you want as quickly as possible. We'll talk about this in coming videos. Don't worry. Another reason developers love Spark is its super user friendly APIs. You can filter, group, sort, join, aggregate data with just a few lines of code, unlike MapReduce. This means you can go from idea to result much faster than with older systems. But what really makes Spark tick? It's something called our big brother RDD. Not RGB, the director, RDD, or resilient distributed data set. Okay, I have mentioned this multiple times now, and you might be thinking like, got it. RDD is our big brother, and his name is resilient distributed data set. But what is it? Okay, think of it as a special kind of data structure, like a list or an array that lives across many machines in your cluster, not just on your laptop. And guess what? RDDs are immutable. What does immutable mean? Once you create them, you cannot change them. You can copy them, but you cannot change them. Right? You can copy them, you can transform them into something new, but you cannot change them. That's our big brother RDD. Okay? Here's a great way to visualize it. Imagine you have 3 machines. Each machine stores different pieces, and we already know that it's called partitions, but it stores partitions of your RDD. For example, machine 1 might hold partition 1 and 2. Machine 2 might hold partition 3 and 4. Machine 3 might hold partitions 5 and 6. By splitting the data up, Spark can process everything in parallel across all the machines. That's where the speed comes from. Now, just based on what I told you, you already know that RDDs are awesome. But what really unlocks their power are what we call higher order functions. These let you manipulate your RDDs to do whatever business logic you need. What are those functions like map? Then you have something called flatMap, reduce, filter, and many more. Here's the cool part though. These functions take other functions as argument, often written as something called lambdas. We'll talk about them, right? But little little anonymous functions. Let's check out a quick example that does a word count. We have seen word count using MapReduce. I should have showed you the MapReduce code, but no, don't worry. And I'm not going to execute any code right now because that wouldn't be nice since I didn't explain you how to the installation yet. So I will just going to write it. Don't worry about what I am writing it. Just assume that I am writing some code that will work. Folder, let's say some folder, and let's say the file is readme.md file. And what are we doing? We are doing word count. Lines, which is where we store the data. Then I'm using a function called flatMap, and then I will write a lambda. Come on. I'm like, it's going up. How can I write it? Okay, lambda. Don't worry, when we get to code, I won't be writing with my hand. I will type it. Actually, you know what? Let me do that right now. Okay, maybe that you will. Oh, wow, I need to really zoom or what? Oh, I zoomed that much. Hmm. Okay, so this is the code I'm trying to write. Okay, I'll explain you. Let me just write it first. How many lines is this? 3 lines. Compare that with a MapReduce code, which you would have to write 100 lines for the same thing that we did here. So the first line, we load a text file into Spark with something called sc.text files. Okay. This returns an RDD where each element is a line from the file, right? This returns an RDD and each element is a line from the file. If the file has 10 lines, each element will be one line. And then we are using flatMap with a lambda function. And by the way, this coding is in RDD, which is like in the beginning we used to do that. We don't have to use this functions and etc. Right now we can use higher not higher functions, high level APIs like Scala and PySpark and whatnot. They will be completely different. So So for every line that the file had, we split it into words. That's what we are trying to do here. Okay, and there is a space between here. I missed, I didn't do that. This transforms our RDD of lines into again an RDD of words. That's what we are doing. Remember our example, if we had a cloud space computing, this space, this splits cloud into one word and splitting into another word. And finally, the third line, we are using the map function to turn every word that we had here into a tuple. Tuple is like a key value pair again. Okay. Where you are going to have S is the word that you have from here. So you are going to have word comma 1. This sets up perfectly for counting each word. And as you can see, this is super intuitive compared to the clunky hundreds of MapReduce lines our way of doing things. Okay. This, when we install Spark, we can execute it later on. But right now, I think this is what you need to know. But if you are thinking, okay, fine, now I know, but why are they called resilient distributed data sets? Well, because Spark tracks something called lineage. Remember the lineage we spoke about? That's why I said it is very important. Spark tracks this. Every RDD knows exactly how it was created. If you see, here you have another RDD, right? This knows how it got created. It knows that it got created from this got created from there. Step by step, all the way back to the original data source. Why? Because if one machine fails and loses some data, Spark can automatically rebuild just the missing pieces using the lineage info. This is what makes Spark incredibly fault tolerant. Even if there is a failure, it can still recover. That's what fault tolerant means. Now let's take a step back for a second and rethink how our MapReduce, which was before Spark, which was the king of big data, right? And we already know MapReduce had big problem. What is it? It didn't like to share. So let me show you another image that I stored here instead of me drawing. Let's say you want to answer 3 business questions from your, let's say you have a web store and you wanted to answer 3 business questions from your web store's activity data. And what are those? Number 1, how many unique users visited today? Number 2, what's the average number of items in cart? Number 3, what are the top 10 most popular products? Now, if you had to write MapReduce code, you would have to write 3 separate jobs. Each job reads the same data again, correct? Because you are asking 3 questions, but you have to you are reading the same data set but asking different questions. If it is MapReduce, you have to read in your, because you are going to have 3 different jobs, right? You cannot have all this in the single job. You cannot do that. That's the problem of MapReduce. You have to have 3 MapReduce jobs, which means each job will read the same data again. And it does its processing and writes the results. This is slow and wasteful, right? Reading the same data set 3 times. But our hero Spark, it changed it. With RDDs, you can load the data once, then run multiple transformations and actions on it, all in memory. This massively reduces repeated work and makes your analytics pipeline much faster, right? This is the MapReduce job. You can see, right? For unique users, you will read the activity table and you will say count distinct, and then you will say give me unique users in the daily. Another job, same thing, you will read the same activity, but you are performing another reduce function, which is average sum of items. For this question, same again, 3 times you are reading the same file, and here your reduce function will say item sum of items, give me that. Okay. Now let's go back to partitions, right? We mentioned that RDD is nothing but you store the data into partitions on different machines, the same data. Imagine you have a 1 GB file and you want to process it faster. If you split it into 10 partitions, you have 1 GB file divided by 10 partitions. Each partition is what? Then 100 MB roughly, correct? Each machine in your cluster only has to process 100 MB of data. Partitions are like chapters in a book. Each node takes a chapter and everyone reads in parallel. So you can imagine, right? If a single person reads 10 chapters, each chapter, let's assume, takes 1 hour, it takes 10 hours. But let's assume that each chapter is read by 10 people. So it will take 1 hour. You can imagine every step is recorded, right? So what did we say? Lineage. Remember that RDDs don't actually store your data. I didn't mention that, but RDDs, they don't store your data. Then you are like, huh, you just said you partition it. How come you are saying they don't store your data? Well, I said they will be partitioned, but I never said the data. What it stores is the instructions for how to get and transform your data. It will have the instructions like, okay, this data in this place should be partitioned and put it here. It has the instructions. It's like a blockchain for data processing. Every step is recorded. If something goes wrong, Spark can replay the steps to recover. Okay, since RDD doesn't store data, each step, the 3 lines you have seen, nowhere it stores the data. They are just logical code stored. That's it. That's the another awesomeness of it. You will learn about it. This makes Spark both efficient and reliable. If you cache an RDD, Spark can reuse it for multiple analysis without going back to the source every time. By the way, caching isn't always needed. If you only use your data once, caching wastes memory. But if you are going to run multiple queries on the same data, caching can save tons of time. Now, let's recap. This is too much information, so let's recap and see what we spoke about. Spark is fast because it works in memory and uses smart optimizations. What are those smart optimizations? You remember? Lazy evaluation and partitioning, correct? And what is the other one? Even I don't remember. Predicate push down. What is that? We will learn about in coming videos. RDDs are the core building block. Think distributed, resilient, and parallel. RDDs, right? Resilient, distributed, and parallel. And we spoke about higher order functions like map, flatMap, and filter. They make data transformation simple. RDDs remember their lineage, which means they are resilient to failures and can be rebuilt on the fly. Spark lets you avoid the repetitive slow steps of MapReduce, making your data workflows faster and more efficient. In our next video, we are going to dig much into Spark, okay, and etc. Spark architecture, which is going to be very interesting. And if you found this breakdown helpful, give a like and subscribe for more deep dive into data engineering and Spark, and let us know in the comments what you are curious about next. Thanks for watching, and don't forget to do the quiz as well as interview questions. See you in the next video. Peace out and love you all.